In section 4.6, we're going to talk about solving our higher order polynomial equations again. This time, though, we're going to be using graphing technology to do so. We know that sometimes, no matter what we do, we just can't factor our polynomial. And sometimes, even though we might try the rational zeros theorem, it's possible that there simply are no rational zeros, in which case we really don't have a good way or any way to solve our higher order equation by hand. So in that case, we're going to have to rely on technology. Now, how are we going to use a graph on a calculator, the Desmos for us, for the computer, to find the zeros of our polynomial? Just like we did with the quadratics, my suggestion is that we start by taking whatever equation we have and making sure that it's equal to 0. So if we're just asked to find the zeros of a polynomial, we can simply graph it and locate the x-intercepts. Right. If we have an equation, we want to keep that idea of finding the zeros. And so in that case, we're going to go ahead and get our equation in the form f of x equals 0. Might need to do a little algebra to get it there, but once we have that, then once again, we can graph and locate those x-intercepts. Keep in mind, same things again that we learned before about quadratics. We're only going to find what kind of zeros, right? We're only going to find real valued zeros. We cannot find the imaginary ones. Using graphing technology. And of course, that's because, as we saw when we were graphing, the imaginary zeros don't give us any x-intercepts. Now, based on what we know about the degree of our function, we can predict the existence of imaginary zeros, but we can't actually find them this way. All right, so let's give this a try. In this first one, we're just given a function, fifth degree function. We're going to use graphing technology and we're going to produce a graph of the function, and we're going to make just a very rough sketch that we can work from. So here we go. I'm going to pop over here to Desmos and graph this. X to the fifth minus 3x cubed plus 4x squared plus x minus 7. Did I get everything there? I think so. All right, so we have this somewhat strange shaped graph. By the way, one really quick check you should always do is we should always, check to be sure we think we've got the whole picture here. As a fifth degree equation, I know that the end behavior should be like x to the fifth, so down to the left and up to the right is appropriate. I probably am seeing everything I need here. All right, I can see 3 x-intercepts corresponding to 3 zeros, and I'm going to go ahead and I'm going to draw just a very rough picture of what I'm seeing here. And then all I'm going to do is label those x-intercepts. So it's approximately negative point. Let's see, later on it's going to tell me to round to the nearest hundredth if you look down at part B. So I'm going to round to the nearest hundredth as I write these down. So I'm going to be writing down negative 1.96, comma 0. And the next one, negative 1.18, comma 0. And the last one, 1.44, comma 0. So this is what my paper looks like right now. Again, very, very rough graph. The thing I'm really interested in are those x-intercepts. All right, so I'm going to say, since there were 3 x-intercepts, there are 3 real zeros. X equals negative 1.96, x equals negative 1.18, and x equals 1.44. Now we know those are all rounded off values. We rounded to the nearest hundredth. The exact values are probably decimals that go on forever. They're probably square roots or cube roots or something that we just don't know at this stage. We can't find that out using the graph. So, since I found 3 real zeros, and I know there should have been 5 zeros in all, that means that there must be 2 more imaginary ones. So we need 5 see if I can get this so I can show you everything I want. There we go. We know that we need 5 total zeros. 3 of them we've already found were real. That means the other 2 must be imaginary. Keep in mind, imaginary zeros always occur in conjugate pairs, right? So those 2 imaginary zeros are a pair of an imaginary number and its conjugate. Can I find them? No. I can't find them. All right, let's try a couple more. In each case, we're going to include a rough sketch to support our answer. This time, instead of just finding the zeros of a function, I actually want to solve that equation. So the first thing I want to do is turn that equation into something that's equal to 0. So I'm going to say I have my 3x cubed plus 4x squared. And then I'll have a minus 18x and a plus 5 equal to 0. And I'm going to graph this cubic polynomial. So here we go, 3x cubed plus 4x squared minus 18x plus 5. And I'll be sketching what that looks like, and I'll specifically include these 3 x-intercepts that I'm seeing here. So again, a rough sketch is sufficient. My first x-intercept, we're rounding again to 2 decimal places, so I'm going to call that negative 3.30, comma 0. The next one over is just 0.30, comma 0. And the last one, 1.67, comma 0. So the graph that I'm using to support my answer just looks like that. Again, a rough sketch. The x-intercepts are the only things that are really important. And I'm going to say my solutions then would be x equals negative 3.30, x equals 0.30, and x equals 1.67. All right, does this equation have any imaginary solutions? Well, since this is a cubic equation, 3rd degree here, and we already have 3 real valued solutions, That means there are no imaginaries, right? We found them all. All right. What about example 3? Once again, I've got an equation to solve, and I'd really like to turn that just into a function equal to 0, so I can use those x-intercepts again. So I'm going to go ahead and multiply this out. It just helps me to see the degree a little bit better. I have 3x cubed minus x to the 4th. And then to get a 0, I'm going to have to subtract 4x squared, subtract x, subtract 5. There are no like terms, but if you want to, you could certainly rewrite this in descending order. Excuse me. Just to make it look a little bit more normal, and kind of helps us to identify the degree and all that good stuff. So in fact, this degree is 4. And we'll go ahead and check out the graph. All right, I'm looking at this, and I might wonder whether I'm seeing everything. I think I probably am, right? This x to the 4th, that would be the parabola-like shape. So up to the left, up to the right. But with the negative leading coefficient, that would tip it upside down. So down to the left, down to the right. I'm probably seeing everything I need. If I'm not sure, I can always zoom out a little bit. But it becomes pretty clear that thing's not going back up again, right? I think I've got it. And you'll notice that this graph never crosses the x-axis. So I'm going to make a sketch of what I see here. Doesn't have to be all that accurate. Right? Just something that basically doesn't cross the x-axis. And because it never crosses the x-axis, there are no x-intercepts. So there are no real valued solutions. Okay. Well, I do know that as a 4th degree polynomial, I should have a total of 4 zeros. And since I had no real ones, that means I must have all 4 imaginary. I'm going to double check myself. Again, they always occur in pairs, conjugate pairs. So that would be like 2 pairs of imaginary solutions. So that makes sense. All right, we've got just a couple more here. In example 4, let's see here. Again, I've got something that's not equal to 0, and I might as well multiply that out. So I've got a great big long equation here. The other side would be 22x squared minus 22x. So if I take these 2 terms and bring them over to the left side to get the 0 that I would like, let's see, right in there I could put my negative 22x squared, and that'll come over as a positive 22x, and then finally that minus 8. So I got this great big long 6th degree polynomial here. And I'm going to go ahead and type that in, see what the equation graphs like, or what the function graphs like. All right, there it is. All right, just at least enough so I can kind of see the whole thing. And I am pretty convinced that this is probably everything. As a 6th degree polynomial, even power, the up to the left, up to the right makes sense. So I don't think I'm missing anything. And I am seeing a 0 right here, and another one right there. So let me sketch that. Let's see, this first one was at -4, 0. And the second one is at 1, 0. All right, so clearly I have a 0 at x equal -4 and at x equal 1. But something kind of interesting happened this time, right? Look at this 0 at x equal 1. The graph does not cut straight through the axis at that point. In fact, because it's got that little inflection point or that little wave, that has a higher multiplicity. It's not a multiplicity of 1. It has to be an odd multiplicity, so I'm going to say it's probably a multiplicity of 3. The -4 cut straight through, so that one was a multiplicity of 1. Now, I'm going to be honest, I can't be 100% sure that's not multiplicity 5, but I think it's probably 3, and I'll explain a little bit more about that in just a minute. Okay? But hopefully you're understanding why it's not 1 or 2. 2 would be a bounce off, right? It's got to be at least 3. So, including multiplicity, I've found 4 real zeros. I should have a total of 6. We found 4 real, including multiplicity. And that means there are 2 imaginary. It wasn't a bad assumption to say I think that's multiplicity 3, but I want to think about something for just a moment. If that had been multiplicity 5, I would have found all of the real zeros, or all the zeros would have been real. I would have had multiplicity 5 here, plus 1 more, would have given me 6 total, and that would have been it, right? All 6 zeros would have been real. Here's the problem. If all of my factors are either x plus 4 or x minus 1, 4 times a whole bunch of 1s is never going to give me that -8 that I would need. So I believe there has to be some imaginary zeros to create that y-intercept. Now, that's interesting to think about right now in homework or in a worksheet or something. That's a little bit beyond the scope of what I would ask you on a test. So, subtle thing, but just something to kind of notice. All right, we've got one more here. And again, right now, this is definitely not multiplied out. It's not absolutely vital that I multiply it out. In fact, this is kind of a lot of work to multiply out, and it's already equal to 0. So here's what I'm thinking. If we think we can figure out the degree without multiplying it out, then let's not bother. Okay? I'm seeing 3 total terms here. 3 sets of stuff that are multiplied together. And if you look at this first set of multiplication, x to the 5th times 2x times x, that would result in an x to the 7th power. So that term would have degree 7. This one clearly has degree 4. And this one with an x squared times a 2x, that would have degree 3. So the highest power in this whole polynomial is going to be 7. And that's really enough to know. Right? If I know that, I can do everything else. So I'm not going to bother multiplying this out. I'm going to go ahead and put this in exactly the way it looks. It saves me quite a bit of time, right? As well as the potential of making mistakes. So here we go. X to the 5th times 2x minus 5 times x plus 2 plus 5x to the 4th plus 3 times x squared plus 3 times 2x minus 1. Okay, here's my function. I need definitely a different window here. Yeah, that's a bit better. Whoops, a little too far. There, that's okay. All right. So I'm seeing 3 x-intercepts. And again, I'm going to create a sketch of that. Doesn't have to be perfect. Goes up and bounces off. Comes back up and cuts through. Back down and bounces off. The first x-intercept, if I keep 2 decimal places, negative 1.73, comma 0. The next one that cuts through, 0.5, comma 0. And the last one that bounces off, 1.73, comma 0. So my picture just looks like that. Again, it's not a perfect shape by any means, but I've got the important stuff represented here. So, my real solutions. X equals negative 1.73. Now that just touched the x-axis and bounced back off. It's a turning point, so I know that's got an even degree. I'm thinking this has got to have multiplicity 2. That one just cuts straight through. So x equals 0.5 would just have multiplicity 1. And then the positive 1.73, that bounces off again. So that's going to have multiplicity 2 again. All right, so I've really found a total, including multiplicity, of 5 real-valued solutions. Since it was, we agreed, degree 7, and 5 were real, that means there are 2 left over that must be imaginary. All right, so that brings us to the end of section 4.6, using graphing technology to help us solve these equations.